Okay, so now we're going to talk about the improper integral. Now, what do we mean by improper? Well, here's what makes an integral proper. You have an integral from a to b of f of x dx. And here's what I did not emphasize. This is continuous on AB. That's what makes it proper. Okay? What happens when it's not? Like, for example, what if I gave you the integral of 1 over x dx from 1 to infinity? Certainly, we have a continuity problem, don't we? So what are we talking about here? Let's take a quick look at this graph. 1 over x dx from 1 to infinity. It kind of goes something like this, right? Here's 1, 1, 1, and then now, is that area infinity? Or does the area approach something? Now, to a kid who's never had calculus, they would say, well, the area has to be infinity because it's going out forever and there's always area there, right? And in this case, it actually is infinity, but we're going to see 1 over x squared is not, but I'm teasing. Okay, this is an improper integral because of the infinity. So, what do we do to make it proper? Because, you know, we want things to be proper. We change it to the limit as a approaches infinity of the integral from 1 to a of 1 over x dx. Okay, so first of all, do you understand the notation here? Let's just do a dramatic pause and make sure you understand the notation. There's nothing tricky. I haven't really done much other than, you know, change that upper limit so that, you know, the math professors of the world don't get all antsy, right? Because they get twitchy when you start having infinities as your limits. I don't like that. That's not proper. You got to be proper. But the most important question is, what the heck is actually going on with this area? Funny you should ask. What is the antiderivative of 1 over x? I know you all know the answer. You're just not yelling it out. If you said natural log x, you'd be correct. So we're going to take the limit as a approaches infinity of the natural log of the absolute value of x, evaluated from 1 to a. Now, absolute value is kind of moot here because we're dealing with numbers greater than 1, right? So let's keep going. Let's keep playing this game. This is going to be the limit as a approaches infinity of the natural log of a minus the natural log of 1. Well, the natural log of 1 is 0. So the limit as a approaches infinity of the natural log of a, well, what's the natural log of infinity? Infinity! Okay, so this is infinity, and we say, now here's the word we use. We say that this integral diverges. In other words, it does not converge to a number, it diverges to infinity. Now, you're going to hear that word a lot in the next couple of months. But we say this integral diverges. Okay, this is an example of an improper integral. But far be it from me to show you an integral that diverges without showing you an integral that converges. And don't get me wrong, every integral you've done so far is converged, right? It's converged to a number. That's the answer. That's what it converges to. I want you to pulse about the next question and the difference entre this question and the next one. Okay. 1 over x squared from 1 to infinity. Ha! Now, quelle est la différence? Well, 1 over x is special, isn't it? Because we can't use the power rule with it. We got to go to natural law. Okay, well, first of all, we're going to write this as a proper integral. All right, so you go ahead and do that. You go ahead and do that. If you wrote the limit as a approaches infinity of the integral from 1 to a of x to the negative 2 dx, that'd be nice. Now, why did I write that as x to the negative 2? Because that's how my p-brain works. All right, now, what do we remember? Back in our p-brains, we know, right, the power rule for integrals. Power rule for integrals. And I'm sure you know this by now because every introductory calculus student has to know this. Right? Everybody knows and loves that formula. Right, Maxie? We love that formula.
Yep.
So here we go. Let's do it. So this is the limit as a approaches infinity of x to the negative 1 over negative 1 evaluated from 1 to a. Now I'm going to put on my algebra pants and now rewrite that so it looks like something I know how to do. The limit as a approaches infinity of negative 1 over a minus negative 1 over 1. Well, now look at the difference. What is the value of this as a goes to infinity? If you said 1, you'd be correct. What's going on here, right? You got 1 over a really, really, really big number. That's 0. 0 plus 1 is 1. So this answer is 1. What does this graph look like? Well, 1 over x squared is very similar to 1 over x, but what's the difference? It's just a little bit tighter. Okay, and this is a problem that we're going to encounter again later on in this class. But essentially, 1 over x is your cutoff. Anything inside of 1 over x converges, anything outside of 1 over x diverges when written in this form. This is called the p-test for those of you who've already failed Calculus 2, right? But there's a group of family of functions written like this. And basically, this is what you got. Okay, so here's 1 over x squared. I want you to compare 1 over x squared, 1 over x, and then we're going to talk about the difference for a moment here, and then wrap this up. So let's compare these two. Let me get rid of the fluff here. Okay. So just take a deep breath and compare these two. The graphs are not drawn to scale, but I want you just to compare them long enough to think about it. And I'm going to do, you can pause the video and stare at these. Okay. Now you've paused it and stared at it for a while. Now let's talk about the difference. Okay. So let me wrap this up. Okay, so there is a family of curves. F of x, 1 over x to the p power. Now, you don't even necessarily have to write this down, but I just want you to watch. Here is the center, 1 over x to the first. Now, inside of this, Our curve's like 1 over x squared, 1 over x cubed, 1 over x to the 4th. Do you agree with that? Those are inside there. All of these converge. They have values for their area going out to infinity. Okay? Out here, and including this curve, these would be curves like 1 over root x, 1 over x to the 3/2. I'm sorry, negative 3/2, right? You might have, well, actually, x to 3/2, that's stupid. Let's go 1 over x to the 1/3, 1 over x to the 2/3, right? They're all outside of that. Do you agree? The side based on the size of the exponent. These all diverge. Diverge, meaning they go to infinity. These converge to a value. Okay? And the cutoff is 1 over x. So basically we say, look, if f of x is 1 over x of p, then the integral from 1 to infinity of 1 over x to the p dx diverges p less than or equal to 1, converges p greater than 1. Okay, now this will haunt you later on in the course when we study convergence and divergence, but just so you know now, this is the idea behind the improper integral. Now, are there other improper integrals? Of course there are, and I'm sure you can think of them. How about maybe 1 over x from -1 to 1? What's the problem with this integral? What's the problem with that integral? Why is that improper? So think about it for just a second. Why would this be an improper integral? Because is there an x value on that between -1 and 1 that's going to cause me problems here? Yes, there is. Yes, there is. 0, right? This is not defined at 0. So therefore, we have to come up with a couple of different ones. We got to go the limit as a approaches 0 of the integral from -1 to a of 1 over x dx, plus the limit as b approaches 0 of the integral from b to 1 of 1 over x dx. And then you rock that out using your natural logs. Okay? But we have a problem there. Okay, and that's how that works. Okay, so spend some time doing some improper integrals, evaluate some limits, and understand that this use of the natural log and this use of the power rule for integrals, right? Remember the power rule for integrals, x to the n dx only works if what? N is not -1. Because when n is -1, we have a 0 in the bottom. What happens when n equals -1? You got natural log. Improper integrals. Have some fun with them. They're your friends.